But okay, I guess you can read from the slides or somewhere. I hope so. Okay, yeah, and let me also, so acceptance is the problem you given a word, an automaton you want to know the word is accepted as automaton. Containment would be I give you two different automaton and I ask you is the language of the first one contained in the second one. So it's a more general problem. Equivalence to languages, to automaton, and to the recognize the same language. So all of those operations are efficient in the deterministic world, but in the NFA, some of them are difficult. So the acceptance problems, this can be done in quadratic time, and we have an OV law bound for this, but containment and equivalence are actually p-space complete in a general NFA case. All right. Yeah, but we still like NFAs because they are exponentially more success. So what I mean by that is that I would need less states to express the same language. So I told you they could express the same language, but if I convert an NFA to a DFA, so now I'm only allowed with deterministic transitions, I might have an exponential blow. So that's actually a good example. So here I have an NFA because of this non-deterministic transition around the state S, but for this this non-determinism is used to guess which is the one that starts this chain of last n letters. And so here I only use like a linear size NFA to express this language, and expressing this same language in a DFA would require an exponential number of states. So this is why we sort of want something that is like an NFA, and we want something that's succinct, but we want to be able to apply to do all those operations and solve those problems efficiently. And so if you look a bit further what differentiates a DFA from an NFA, you can look at how many runs are actually accepting. So I told you that the word is accepted by my NFA if there's at least one run from a starting to a final state. And then the NFA word, because I have those non-deterministic transitions, I could have a bunch of those accepting runs, right? But in the DFA word, because it's deterministic, I only have exactly one accepting one. But actually, this example, you see that if I give you a word in that language, well, you know exactly which is the run that led to an accepting state, right? So even though it's non-deterministic, it's pretty clear what run, what path led to the accepting state. And this is the measure I'm going to use to quantify how much of a DFA or how much of an NFA I am. So let me define this notion of ambiguity. I'm saying an NFA is unambiguous if a word has at most one accepting one. As a zero, it's not accepted, but if it's accepted, exactly one accepting one. And this builds the class of UFA, so the unambiguous finite. And well, UFA is still more succinct than DFA, right? This example, this was unambiguous, and this is a good example where you would have a super polynomial blow-up to convert it to a DFA. And actually, what was proven is that if you are guaranteed that your NFA is unambiguous, then you can solve containment, equivalence, all of those problems efficiently. So we would like to be able to work with UFAs. And actually, let me expand this definition a bit. Maybe I'm not bounding the number of accepting ones by one. Maybe it's a constant or a polynomial in the word length. And this respectively defines the finite ambiguity and polynomial ambiguity of an NFA. And so the classes are FFA and PFA. And I have this natural hierarchy, right? Like if I'm deterministic and particularly unambiguous, which in particular means you're finitely ambiguous, etc. And actually for every pair of this class, we can find a language that shows exponential successiveness. So it does matter to look at those classes differently. All right. So now the problem I want to solve is given an NFA, is it unambiguous, finitely ambiguous, polynomially ambiguous, or not at all? Like let's say exponential ambiguous would be if you're not polynomially ambiguous at all. Basically, I'm given an NFA, and when I want to place it in the right class here. And well, this was shown to be polynomial time solvable in the 90s, and then later on it was shown that we can solve unambiguity, decide unambiguity or polynomial ambiguity in quadratic time. finite ambiguity in cubic time. Yeah, and what we showed in my co-authors is that those bounds are actually typed on the orthogonal vector hypothesis or the K-cycle hypothesis for the quadratic bounds and under the 3OV hypothesis for the cubic bound. And so today I'm only gonna focus on those quadratic results. I'm gonna sketch a bit how the algorithm works. They are not very complicated and gives you an idea of how you actually decide this. And then I want to show you the double bounds from OV and K-cycle. Yeah.
So is it intuitive that the finite case is harder than the polynomial case? Because
yeah,
the polynomial case is more general. So
yeah, so it's more like so to decide if you're unambiguous, you're gonna check if you have one run or more. And to decide if you're polynomial ambiguous or not, you're gonna check if naive upper bound would be an exponential number of runs. And so basically to check if you're here, you're just gonna check, do I have an exponential number of runs or not? So it's more like to check this, you check, are you outside of it? And then here it's very intuitive, all of this, but it's more like a refinement. Okay, I'm polynomial ambiguous, but what's the polynomial? Does it have degree 0 or? So that's why it's a bit more complicated. Yeah. Okay, so to present you the algorithms, let me recall some basic operations I can do. So first, I can assume that I have a single starting state and a single final state. Just add a super starting state, a super final state, add the transitions I need to. This makes stuff simple and doesn't change the language that's accepted, doesn't change the degree of ambiguity. And I can also trim it. And what I mean by that is I want that every state in my automaton is both reachable from the starting state and co-reachable from the final state. So if I have a state like this, well, it will never be visited by any of my accepting run because it's not reachable from S, so I can just forget about it. And similarly, this state, even though I can reach it, starting from S, it will never lead to an accepting run. And I'm just focusing on the accepting run, so I can forget about this state. And okay, running DFF, you can trim an automaton quite efficiently. And another operation I need you to recall is the intersection of NFAs. And I think this is clear by just some example. So I have here two NFAs that recognize the language that starts with A ends with B, language of all the even length words. And when I take the intersection has the state for every pair of states from the two first. And I have an edge between pairs of states if I had the corresponding states in the original NFAs. So here, for example, I have this transition reading B because I had in the original a transition from S to F in A1 and also from F prime to S prime in A2. Okay? And so naturally, when I take the intersection of NFAs, the language of this guy is the intersection of the language of the two previous guys. Okay, so now these are basically the only tools I need to decide if I'm unambiguous or unambiguous. And to decide if I'm unambiguous is super simple. So what I do is I just take the intersection of the given NFA with itself, and then I check if all my states are of the form QQ. So I remember in the intersection, a state is a pair of states, so PQ, for example. And say if in this intersection automaton, I have the state PQ, because it's trimmed. Of course, when I take the intersection, I can trim everything. It's reachable from the state SS by some word U, and co-reachable by some word V to the state FF. So here those wiggly arrows mean a path. This could be multiple transitions. And so now if you assume that P is different from Q, what this means in the original automaton, by the definition of how I take the intersection, this means I had the corresponding transitions or path reading U from both S to P and S to Q, right? And similarly for V. Now this means that the word UV will have two accepting paths in the original automaton. So I'm not unambiguous, I'm ambiguous. Right, so basically I just need to check that in this A square automaton, all the states are of the form QQ, like the same state twice. So I do it pretty simple. I compute intersection, I trim it, and I check this. Okay. Now for polynomial ambiguity, this is going to be slightly more complex. So as I mentioned, I'm going to want to determine what allows the automaton to have an exponential number of accepting ones. So instead of quantifying what's polynomial ambiguous, I'm going to quantify what is not polynomial ambiguous. And this is actually this EDA structure, which stands for exponential degree of ambiguity. Basically, I'm just saying that an NFA has EDA if you can find a state Q with two cycles reading the same word W, so two distinct cycles, or walks. It could not necessarily a single cycle. And so what I'm claiming is that if I have this structure, then I cannot be polynomial ambiguous. The one direction is quite easy. So if you have this structure, of course, I'm working with trimmed automaton again, then the state Q is reachable by some word U, co-reachable to F by some word V. And then using the structure, you can pump an exponential number of accepting ones, right? If you have the word U, W raised to the power T, V, then each of this W, you have a choice which of the two cycles, red or blue, you use to read the word. And I mean, the other direction, let me not put it here, but basically, if you don't have the structure, there's not so much you can do to traverse the graph. You can only have a polynomial number of accepting ones, and you will not get this exponential number of accepting ones. But yeah, let me not get into this, and believe me on this one.
Is there like an absolute upper bound of the degree of the polynomial then?
This is no. This people are interested in that. So there are different structures you can test, which would tell you how much. Yeah, this is actually one of the still open problems because people in that community don't care so much about this, right? They work with higher classes. But that would be like I would be quite interested.
So those depend on the automata size. Like
Yeah, so sorry. When I so this polynomial is in the it depends on the size of the automaton. And when I say polynomial is in the word length. So I can have something 2 to the power n, where n is the number of states, but this is still constant with respect to the length of my
can you say something like at most, I don't know, the word length to the power of automata size?
2 to the power of the word length would be like a triple. Yeah.
But I think what we need is the polynomial in the automata. I mean,
So
you say that there are no bounds or that there are no interesting bounds?
there are no interesting ones.
Okay.
Yeah.
So you can say something using the automata size.
Yeah, I mean, something like 2 to the n times the word length, or like alphabet size or something like this. Yeah. Yeah. Okay, so back to this polynomial ambiguity testing. So basically what I want to check, I want to test if I have this structure, this EDA structure. And again, I'm going to use this intersection trick. So I'm going to take the intersection of A with itself, look at the trim version. And now I look if I have two states, QQ and PP prime, that are reachable from each other. Let's say from some word U and V to come back. So if P and P prime are distinct, what this means in the original automaton, again, I need to recall how I built my transitions. This means that I had a walk from Q to P and from Q to P prime, reading the same word U, and conversely back to Q, reading the same word V. Right? So if P is distinct from P prime, then I have exactly those two loops that read the word UV. Right? So again, this is quite simple. I'm just checking for EDA means I'm computing this intersection automaton. I'm checking for the structure and basically computing the strongly connected components. And then I can determine it for all right. So those were those two quadratic algorithms. Are there any questions before I move on to the lower part? Okay. So now I tell you I'm showing you that this is titled the OV and on the case cycle. Actually, I'm going to show you that unambiguity reduces to polynomial ambiguity testing. And polynomial ambiguity testing from the previous slides, well, means I'm checking if I have the EDA property or not, right? This construction is quite simple. So I'm given an NFA. I want to check if it's unambiguous. And to do so, I'm just gonna add a feedback loop from the final state to the starting state that reads some new letter, let's say dollar. And I'm gonna ask if this augmented automaton has the other property. Now I'm playing this is equivalent for the original automaton to not be unambiguous. So let me show one direction. And so let's assume A is not unambiguous. This is a new concept. So let me recall what this means. It's not unambiguous if there's a word that has at least two accepting marks. So two walks from S to F by labeled by this word W. So now if you just extend those walks from S to F by using this feedback transition, you get two loops around S, right? And those two loops read the word W dollar, and those two loops are the same. So this was exactly the setup property. So now assume this augmented automaton has the other property, meaning there's a state Q that has two distinct loops around it reading the same word W. Now there are two cases. Either the word doesn't contain the dollar sign, well then it's easy because then the structure was already present in the original automaton, but more simply then UWV would have at least those two accepting ones. So you're not unambiguous. You have at least two accepting ones. If it does contain the dollar sign, then this means that from Q you actually went to F, then you use the feedback loop to S, and then you continued all the way up to Q again. And you might use the dollar sign multiple times. So let me just cut the word into the chunks separated by W, by the dollar sign. And see that those are actually loops around Q that will necessarily go through the state S. So I can just see them as loops around the state S, right? I can just shift the whole perspective. And that picture, this just means that what I do at the beginning when I go to F and then take the feedback loop, let's just say that this is what I do in the end. Just put this in the back. And so now again, a bunch of words for which I have a run from S to F, and those are separated by dollar sign. But because those two original cycles were distinct, this means that there is one of this word, one VI, for which the two loops were doing something different. So for this VI, I had two different accepting ones, which means I'm not unambiguous. All right. And in this reduction, I'm not losing anything in the size of the automaton, right? So I have this simple reduction from unambiguity to polynomial ambiguity. So now I want to show OV and K cycle bonds. And actually, let me introduce some other intermediate problems that's going to make stuff simpler, the disjointness problem. So here I'm getting two DFAs, deterministic finite automata, and I'm asking if the language of their intersection is empty or not. So this very easily reduces to ambiguity because I can just take the union of the DFAs. Yeah, so the union of the state, union of transition, etc. And if you see that in that union, a word is accepted if and only if it's either accepted in the one DFA or in the second DFA, right? And because these DFAs are deterministic, in particular they're unambiguous, they can provide at most one accepting one. If I have two accepting one in this union, I have an accepting one in each of them. So the word is accepted by both. All right, so disjointness reduces to unambiguity by this very simple reduction, but I like this problem because now I have to work with DFAs. So when I reduce case cycle, for example, to disjointness, now I need to design a deterministic automaton, which is way simpler to designing something that then I need to be proven to be unambiguous. Okay. So let me move on to this case cycle lower bounds and let me recall what the problem is. So given a graph, K type with like A1, A2 up to AK sets. And you want to decide if you have a cycle of length K. Basically, if you have a cycle from A1 to A2 to AK up to A1. And the hypothesis is that this cannot be solved in subquadratic type and the total number of edges. And to reduce this to disjointness, I'm gonna use the fact that because in disjointness I have two DFAs, I can check for two properties simultaneously. So I'm saying that a K cycle is both a path of length K and a cycle. So a path of length K means I start from A1, from the set A1, I traverse all my partitions and I end up in A1 again. And so this can be checked by, basically I'm just gonna copy the whole graph. So in this example, I have a graph with three partitions A, B, C. I'm going to copy everything and I'm going to orient my edges from the set A to the set B, to the set C, to the set A. And I'm going to label my transitions by the incoming guy of my transition. So for example, when I move from the vertex B2 to C1, I'm going to label this by 1 because I end up in C1. And so now in this part of the DFA, if I have a work from one of this column to one of this column, this exactly means that I have, in this case, path of length 3. So path of length K for the general case. So I started, for example, from A2, I moved to B2, C1, A1, but this is exactly a path of length K. But this is not a cycle, right? I started from A2 and ended up in A1. So I also need to check that the first and last vertex was the same. And this is where the second DFA comes into place. So the second DFA needs to remember what was the first vertex I explored. So I'm going to start actually my whole world by branching on which of the A1 vertex I'm starting from. And then the D2, the second DFA is just not going to care about what letter is read next, and it's just going to move to the next state. And this way, it's going to remember what was the first letter I read. And at the end, only accepts the word if the last letter is equal to the first one, which would mean last vertex is equal to the first one. So here I'm using this wildcard transition to mean that for any word of the alphabet, I'm transitioning. Well, and then, well, this construction, okay, first maybe, I hope it's clear that if I have a word that's accepted by both, then I have a K cycle. If it's accepted here, I have a K path. If it's accepted here, I have something that would also be a cycle. First and last is the same. So together they witness that I have a K cycle in the original graph. And here I just copied the graph, right? So I only have a linear number of states and transitions. But there's a cheat, right? I use this wildcard transition. This wildcard transition means that I accept any word of my alphabet, and here the alphabet is the ID of the vertex in my partition. Typically, the partition would have n vertices, and so this transition needs to accept n different letters. The naive way to implement this would require n transitions, and this would be too much in our reduction. But this is actually fine. We're computer scientists, so we can just binary encode this thing. We just put a chain of log n states. You accept any 0-1 transition between them. So equivalently, when you have, I don't know, transition reading 2, you have this log n chain and you read the bits from the encoding of 2 in this binary encoding. So this would occur only a log n blow up in the number of states and transitions, which is totally fine for this type of reduction, right? All right, and so this shows that basically, because I don't believe I can solve K cycle in subquadratic time, I cannot solve this joint in subquadratic time, which transfers to unambiguity and polynomial ambiguity. Okay, maybe 5 more minutes to show you the OV lower bound. So actually, an SCTH lower bound was moved for disjointness. But it was quite elaborate, a bit complicated. We made it way simpler and more general, and so this is why I still want to present you the OV lower bound for disjointness. And I think it's quite clever and quite easy to understand. So OV, again, let me recall. I know we all know what this is, but you're giving a set of n, 2 sets of n01 vectors of a dimension d, and you want to check if you have a vector in A and a vector in B that are orthogonal. And I believe that this is not solvable in subquadratic time. Okay, so what basically I need to do is I need to encode this property that I need to check. I need to encode in this disjointness problem. So let me look at what it means that A is orthogonal to B. This means that for every of the coordinates, either A provides a 0 or B provides a 0, right? That's the definition of orthogonal. And I can see this as either A is responsible to giving the 0 or B is responsible for giving the 0. And so I can actually encode this as a chain of responsibilities for each of the coordinates. So first, let me explain what I want the DFAs to do, and then I'll show you the construction. So basically, I want the DFAs to recognize words of this shape And D1 is only going to care about the choice of A, which is going to be the first character. D2 is only going to care about the choice of B, which is the second character. And then I have those D characters here, which assign the responsibility to either A or B to provide the 0. So if I have for some coordinate L, the responsibility is assigned to A, then D1 has to check that, well, the chosen vector A indeed provides the 0. And similarly, if the responsibility is assigned to B, D2 checks that the chosen vector B provides the 0 at this coordinate. And so now, if I have a word that's accepted by both those DFX, then this means that I correctly assign the responsibilities to A and B, and for each coordinate, I got a 0 in either one of them. So I got an orthogonal vector, right? And the fact that D1 only cares about the A vector, D2 only about the B vector, allows me to avoid this quadratic blow-up that would induce if I would check every pair of vector. And to implement this is very similar to what we've done for the case cycle. So I told you the word starts with 2 characters that implement the choice of the vectors. So D1 with the first character is going to branch on which of the A vector it chooses, and D2 is just going to wait with this wildcard transition. And then D2 needs to branch on the B vector, while D1 waits with the wildcard transition. And then basically, once I reach this point after the 2 first letters, D1 and D2 are on each of branches that correspond to this pair of AB vectors I chose. Now what happens is I'm just going to read the vector I'm in. So for example, if I'm on this branch corresponding to this vector A2, if A2 has some 0, this means that it's okay that the responsibility is assigned to A, because this vector provides a 0, so I accept the letter A. But it's also okay to accept the letter B, because it could also be that for this coordinate B is the one that's going to provide the 0. That's fine. What's important here is that when the A vector has value 1, then the responsibility cannot be assigned to A. So I can only accept the letter B, sort of meaning I defer the responsibility to the other guy. The other guy has to provide the 0. And I do something like completely symmetric for B, right? So when the B vector has a 1, then I only accept the A letter. The responsibility has to be assigned to A. And okay, again, I use the wildcard transitions, but I can use the same trait binary and encode all of this. And then I would just get n times d log n states and transitions in total, which is totally fine again for this type of reduction. Yeah, so basically, if I could solve this one in subquadratic time, then I could solve open in subquadratic time. Yeah, so let me just recap what I talked about today. So I introduced this new problem that I think not a lot of you have heard about, this ambiguity testing. Given an NFA, how much ambiguous is it? And so we have those simple quadratic algorithms. The cubic algorithm works quite similarly. And well, with this chain of reduction, I showed that I have OV and K cycle lower bound. And yeah, I guess some open question would be that, well, this reduction works in the sparse case. We couldn't get anything for the dense case for them. And I mean, as you saw, there's like tons of other problems related to unambiguity where we don't know the exact polynomial, that all of this is still quite interesting and open. Yeah, and thank you for your attention.
Is something known about acceptance of unambiguous automata? I mean, I think acceptance for non-deterministic is quadratic and for deterministic is linear.
But
ambiguity has to decide.
Yeah, so okay, I'm not so sure about this, but I think the OV lower bound for NFA acceptance creates something that's unambiguous, right?
I don't know.
Or you can make it unambiguous. I think so.
Okay.
It was a quite simpler gadget. I think you could make it on.
Which, like, how fast can we check equivalence of 2 DNA? Anyway. or containment?
Yeah, so actually, I don't know. So I know it's going around time because those people said it's going around time, but that I didn't care. And it's actually interesting to look about it. So I haven't been thinking about container equivalence. I've been thinking about universality. So is the NFA accepting everyone? But this is something to end to the 2 omega, like omega is multiplication. But this is like the very naive way to do it, and like I believe you can get something a bit more. Yeah, this is one of the very open.
So I didn't quite catch it, so you are not allowing maximum transitions? But
Yeah,
you are-
that's what, yeah, sorry, but it's called,
but you're still assuming one is the same state. So
yes. I mean,
fine,
I can do this, like those are 2 accepting states, I don't know, and they need A. Whatever, like here I can just have like a direct transition only. If we don't do that. And I can forget about them. Like I don't need epsilon transitions to get a single sum. I think it's like you just need to like write a few examples and you see it's fun. But so yeah, I'm assuming no epsilon transitions for simplicity, but so all of this works also if you have epsilon transitions, but then it becomes difficult because in the intersection you need to take into account how many epsilon transitions we took, or like it becomes a bit messy.